Much, Mark, for the invitation and for the nice introduction. So let me try to share my screen and let us get started. No, that was wrong. Let me see here. Can you see me in full screen mode now? Good, very good. Sorry?
Yes, very good. Please go ahead.
Okay. Okay, so once again, thanks for the introduction. Thanks for the invitation. So since we are not a very large crowd, I will be very happy to have discussions and comments and interruptions, and I will not always be able to watch who raises his hand. So if I'm overlooking you, just shout, okay? There's no problem for me. So the topic the organizers gave me is weak gravity and swampland conjectures. And that's of course a huge field, and I will focus on some aspects which I found particularly important and interesting in the last years and which I worked on. And here in the beginning, you see some of the papers. Let me try to see whether I can have a better pointer. Can you see my red pointer now? Good. So these are some of the original papers that I will also talk about, but most of the stuff will be introductory and review. So I will start with some general comments on the swampland, and then basically there will be three main topics I will cover, or at least in part cover. One is the connection of the weak gravity conjecture and inflation. Two is conjectures about the theta space and possible problems in string theory with the theta space. And three is an aspect that kind of derives from weak gravity, or even predates weak gravity, if you wish. It's the issue of global symmetries in the swampland and wormholes. And I will try to split this into three equal parts. And so there, if you lose me for being too technical in the first part, don't get depressed, and the second part will again be simple. Start simply. But anyway, if you start losing me because I'm too fast, just interrupt. Good. So, introductory remarks on the swampland. So the set of string compactifications is huge but discrete. And since the space of four-dimensional effective field series is continuous, it is clear that not all EFTs are in the landscape. And so there is clearly a swampland. But on the other hand, it is also clear that this is not yet very useful. It's not a very detailed statement. So a key question is, oops, I lost my pointer. I'm somehow not good at this. Okay, let's go on. So the key question is whether, besides the fact that one set of theories is a continuous set and the other is a discrete set, it's interesting to know whether there are general criteria that immediately tell us that a given model is not in the landscape. In other words, that a given model cannot be realized. And the second question is, does this logic work maybe in quantum gravity independently of whether string theory is the right UV conclusion? And finally, maybe the most important question, can we turn things around and use that logic to somehow learn something new about quantum gravity? And so the picture people usually draw is here. You know, you have this big red, poorly defined area of theories which are in some way sick. They may have anomalies, or you forgot to write down some effective operators. And then within that set, there are theories which look completely consistent in every respect. And but they are sick because they cannot be UV completed in quantum gravity. And then eventually, in the core, there's this landscape, a set of theories which are really truly deriving from quantum gravity, as well as being consistent, of course, EFTs in the usual sense. All right, so now what are concrete swampland criteria which allow us to make such statements? So maybe the oldest one, which I will come back in the end of the talk, is that there are no exact global symmetries. I will discuss it in detail in the third part of the talk. The second, historically, is a conjecture about the infinity of moduli spaces and a distance conjecture. And that's a very interesting and important part of the swampland, but I will devote only one slide to it because it's not kind of my main subject and not my main interest here. So what does it mean? So you compactify string theory on some compact space from 10 to 4D, but here I drew for simplicity a torus, something you get when you compactify from 60 to 4D, just for illustration. So the torus has moduli. It can be deformed in various ways. These are massless fields, and so you can go to infinity in that moduli space. And the conjecture is you can always go to infinity in quantum gravity moduli spaces. And you can go to infinity in different ways. You can make the torus very large, in which case the Kaluza-Klein scale goes to 0. You can make the torus very long and thin. You can deform it in this way, in which case also the Kaluza-Klein modes go to 0, because the modes associated with this large circle become light. On the other hand, there are winding strings going around a small circle. Their mass also goes to 0. So in these two ways, the effective field theory breaks down. A third way to go to infinity is you leave the torus what it is, but you take the string coupling, which is a higher dimensional independent modulus, nothing to do with geometry, to 0. But then again, the string scale goes to 0. So you again lose control. So now there are 3 different ways in which you lose control here. And in an actual compactification, it's not a torus. You have maybe some base space, some torus fibered over it. There are very complicated ways in which the torus can degenerate and become singular. And so there are many infinities. And a lot of people, a lot of very good people here, I give for an example, a conjecture by Lerche, Lee and Weigand, study the details of how you approach infinities, how the cutoff goes to 0, how a tower of light states emerges, and so on and so forth, okay? So, but I will not discuss this as my main subject. This was point number 2, and point number 3, and this is the next conjecture I will discuss in detail is the gravity conjecture. Everybody knows, roughly speaking, it says gravity is always the weakest force. But more concretely, for any U1 gauge theory, it says there exists a charged particle with a mass that is smaller than charge times m Planck. And charge here, I mean the combination of the gauge coupling and whatever into the charge the particle might have. So let's go on talking about this conjecture. What is the support? I mean, why would we believe in such a conjecture? So the historical supporting argument is that in the absence of such sufficiently light charged particles, external black holes are stable, and such remnants are believed to cause inconsistencies, due to a paper of Susskind, a very well-known old paper. To be very honest, it is not clear. I think it has not been established why or that such remnants are really a problem. Why shouldn't there be a finite set of absolutely stable charged black holes? But anyway, this is a historical argument, and the reason how it arises is also clear. Namely, if you set m Planck to unity, then this ratio Q over n is 1 is precisely the boundary of stability of external black holes. Namely, if you have a large black hole charged Q equals m, and you split it into 2 with charges Q1 m1, Q2 m2, then precisely at that boundary, if you have the right objects which all fulfill this BPS relation, you can do so at no energy cost. So basically, it doesn't decay. It doesn't have to be forced to split. It just can be smoothly deformed into 2 black holes, basically. So this is considered to be an important point. However, as I said, it's not a very strong point. And I think, personally, but that's maybe a personal opinion, a stronger supporting argument is the following. Quantum gravity, we all know, and I will discuss in more detail, forbids global symmetries. That's a separate statement, which I think is more firm than about gravity. I will come to that. But because global symmetries are forbidden, we should not be able to take the limit of small gauge couplings. This limit should simply not be realizable in physics. So then the regravity conjecture is a statement that attempts to quantify our inability to take this limit on the basis of string examples. Namely, you plot all examples you can construct from string theory, say in 2 dimensions, one side being the coupling, the other being the mass, and you simply realize that you get examples on this side, i.e. for large enough coupling, but you don't get to cross this line. So the expected inability to go to that axis here, in other words, take the charge of the coupling to 0, is quantified on the basis of observation in example model building in string theory. And so you expect then, okay, you simply see this is the right line, the presence of which you expect to be the presence of which you expect anyway. And this has, of course, direct relation to study of complex geometries and string theory. There's much interesting work, including recently, I apologize to Albert Clem, I misspelled his name here. Anyways, this is a recent subject of study. Good. So now it's not obvious that this regravity conjecture, even if true, would in any way impact phenomenology. I mean, there have been some proposals, I list a few authors here, but I think the most accepted and the most studied application is actually to large field inflation in the context of quantum gravity and string theory. Large field inflation driven by axioms. And this requires a further step and a further set of ideas to which I will now come. So, axioms. Let me make a brief detour on axioms. So both in pheno model building and in string qualifications, axiom-like fields are abundant. And for me, an axiom in this talk will be something very general. An axiom-like field, I should say, is just a scalar with a standard kinetic term coupled to instantons. Here, I couple it to gauge instantons, but we will find more general example of instantons later. So here, the coupling to instantons is 1 over f, and trace ff dual is this famous integral that counts instanton number of a gauge field configuration. So basically, the situation that you have is that you have some space-time, and we have a gauge theory which fluctuates. Occasionally, such a fluctuation tunneling process occurs where this integral is non-zero. I will not review the details of this. I mean, I think most people know that. And so this effect of integrating out the gauge theory then breaks the continuous shift symmetry of this field. It has a discrete shift symmetry phi going to phi plus 2 pi f. It is undistinguishable because of the quantization of that number. And then on top of this, you get a potential that breaks the continuous shift symmetry. The discrete one is unbreakable because it's gauged. This point is strictly the same point as this point. So after this preliminary, now how does the regravity conjecture apply to axioms? I'm happy to have interruptions, okay? So if anybody wants to comment or discuss or, just let's be interactive.
So Arthur, Yvonne
yes. Here. Yvonne
yeah.
Hi, nice to hear you. I can't see all the speakers, unfortunately, when I'm
No, that's fine. So can you go back just a few slides? Just I want to ask you, if you go back to some slides, then here. So no, the next one.
This one. This one?
No, when you give a better argument instead of the black hole. Yeah, here.
Okay, good, yes.
Right. So here, I mean, it's, yeah, I'll agree with this. And but in principle, it's assuming that this argument that there are no global symmetries in quantum gravity is true, no? So it's assuming a conjecture to be true already. Isn't that true? So assuming that it's true that quantum gravity forbids global symmetries, then this gives a, then this is a better argument in terms like of.
The short answer is yes. I'm using a different, more firmly believed in assumption, and so I would simply say yes. But on the other hand, I will have a comment. Let me not jump ahead. Okay, I will have a comment on this later on.
All right. Okay.
So I will comment that maybe quantum gravity, maybe we can actually know and show already that quantum gravity doesn't allow global symmetry. So it's maybe not a conjecture. But this is a complicated interplay. So remind me, I will have a slide exactly about your question.
Okay, perfect. And then next one, if you go to your action slide, the first one.
The first one,
Mm-hmm.
the action slide. Okay, this one here, where I simply define. Sorry, this meant very naively, right? I simply explain what an axion is. Okay.
Yeah. So maybe I should come back to the question later. But let me tell you where I'm going. So usually, so I see the conjectures are made about the axions themselves, but usually there'll be a axion, for example. So the decay constant F, the coupling there, will be dependent on this axion. So would you comment on that, or do you know what happens then? What can we say about this?
I will comment on that in great detail.
Okay, perfect.
If in case it will still remain unclear, I invite you to discuss it, because so I can answer very briefly, and then I will answer in detail later on. Roughly speaking, you should think of this F not only as a axion but also as a coupling. It's in fact the coupling of either the axion theory viewed as a gauge theory or the dual B2 theory, and then in the limit that this coupling is taking some extreme values, the cutoff comes down, and I will explain all that. Okay. So I in due course.
Yeah, thanks.
We're happy to discuss more. It's a critical question.
Okay, thanks.
More questions, more comments.
I have another stupid question. Yeah. So in the diagram you show right now in the slide, this field strength, which is non-zero, is it at an instant in time, like an instanton, and it's spread out in space?
It is spread out in time and space by a certain amount, which has to do, roughly speaking, with the details of the gauge theory. In fact, you have also to integrate over the size of the instanton. There's a complicated path integral underlying this, which I'm completely jumping over. So the instanton is, you should think of it really, this picture should, I mean, it's my insufficient ability to draw. It's like a blob, blob spaced out, spread out in space and time by a certain size mu, and that scale mu you integrate over. So there's the smallest and the largest instantons, and which are the most important one depends on the running of the coupling. So there's a whole story behind it, but let's call them, let's be a low energy observer, then it's a point where something happens. Okay, that's the picture I'll take.
Okay, so it's not like an instant point in time.
Well, out by no, it is an instant in time. That's the name instanton comes from.
Yes.
But it is actually spread out by a certain limited amount.
Okay, thank you.
Good, very good. Generalizations. So now I told you the regravity conjecture about two forms, and I write it again. I write the Lagrangian underlying the regravity conjecture. Here's F2 squared. Here is the integral over the world line of the charged particle. The prefactor is the mass. And here is the integral of the gauge potential along that world line. Prefactor is the gauge coupling. Okay? So I'm doing, field theory 101. Now, of course, you can generalize this to other objects, strings, domain walls, and so on, by simply taking not a one-form gauge theory, but a two-form, three-form gauge theory. The field strength then is the P+. So it's a P-form gauge theory. The field strength is dA_P. It's a P+1 form. The charged objects is some extended object. The prefactor is now not the mass, but I call it T for tension. The case of the string is familiar, but you can take branes, etc. And here, for lack of fantasy, I left the name gauge coupling G. Good. So now, of course, this extension, sorry, and I should say that the regravity conjecture simply holds in the same way as before. There's a combination between the tension and the gauge coupling here, limited by the Planck mass. So now one can also lower the dimension of the charged object, making it a point in space-time. Domain wall, brane, world line, point. That is the case of the instanton. So then the action has a kinetic term, which is a one-form field strength belonging to a zero-form gauge potential, which is the axion. Instead of the instanton action, I write here M. It's just a number associated to the existence of an instanton. And then the instanton couples with some coupling G to the value of the axion at that field. You know, a zero form integrated over a point, basically. And this should be compared with the more classical axion, where the kinetic term is the same, but this action comes from the Young-Mills action, and this coupling is the one I just displayed. Phi over f trace f of 2. And this integral over trace f, this integral over f squared is, of course, the action of the instanton, and is what I identified as mass in quotation marks here. So basically, the statement is illustrated in this picture. Like in normal gauge theory, you have some space where gauge potential in u fluctuates, and then you know the path integral has to include some light world lines. In the axion case, you have some scalar fluctuating here, some periodic scalar, and you know you have to have in your path integral these blobs with a not too much, which are not too suppressed, in the sense that they should occur sufficiently frequently. The mass, the action cannot be too high. This is a key point. If this is unclear, anybody should feel free to ask. Okay, now from here, it's easy to go to inflation. First, recall that instantons induce a potential. I already said that, and the prefactor is in fact suppressed by the action of these instantons. Yeah, so e to the minus s times the cosine. Then, for instantons, my gauge coupling is 1 over f. That was clearly visible from the previous slides. The role of the mass is played by the action. So now our weak gravity conjecture, which says mass smaller g and Planck, translates into s instanton smaller and Planck over f. Yeah, g is 1 over f. So directly, so you see this constraint. And now you can control the situation only if the dilute instanton gas is there. If the instanton gas is sufficiently dilute, in other words, the action should be larger than 1. And that implies from this inequality here that f is bigger than the Planck. So s needs to be bigger than 1, and Planck over f needs to be bigger than s. So f must be smaller than Planck. And this apparently forbids large field natural inflation, which occurs if you have a cosine potential with large periods. Otherwise, it's not inflated. But there's more to it. Namely, even if you allow that f is smaller than Planck, this is still a statement. It's a non-trivial statement saying that the action of the instanton is large, is sufficiently large to suppress this exponent. So you see, this e to the minus s factor by this inequality cannot be too small. So instantons kind of always arise, roughly speaking. S being limited from below means that this factor here is limited from below. So it tells you that instantons must be there, even in cases where the axion itself is not forbidden. Again, questions about this? Sorry, before I jump the slide. Important point?
Arthur, I have a question.
Yes.
When you have a particle, you have the stability argument of the extreme.
Yes.
Force. Now, when you promote these two forms.
Sorry, I can't hear you. Can you speak louder? Can you speak louder?
Yes, sorry. When you have particles, you have the stability argument of extreme black holes.
Yes.
For the conjecture. Now that you are promoting it to forms, does the argument still apply? Or
no, I completely lost the Susskind type argument. Except in one case, which is not irrelevant, namely sometimes instantons derive from high-dimensional objects which are wrapped on cycles of a compact space. In that case, the gravity conjecture for those wrapped objects, for those branes or particles in high dimensions, from there you can derive the axion type gravity conjecture in lower dimensions. And it always works, so it's consistent. I mean, but in cases where the instanton finds the UV completion in terms of a higher dimensional charged object, you derive it, and then you can apply the Susskind type argument for the high dimensional object. But in cases where the instanton is thus just there as such, you can't. I think also in the gauge theory case, which I don't want to discuss in detail because I didn't prepare a slide and it's fairly involved. For non-abelian gauge theory case, the axions can never beat, the instantons of the non-abelian gauge theory can never you can never have a theory which violates the gravity conjecture for axioms. Then you have to assume the gravity conjecture for the non-abelian gauge theory, which is a different issue. I mean, there's could be much more to be said, but in the end, you are right. A direct argument like Susskind does not exist. It's not known to me.
Thank you.
Good. So now comes the moment when we really move to more interesting physics. So now the interesting point is not that this is forbidden to have a large field inflation or axion inflation. The interesting point is that actually it may not be true. We may be able to beat that apparently convincing general or not so convincing general argument. And so now let me talk about enlarging axionic field ranges. And so what I want to do is to discuss only one of the three ideas. One is KNP, so Kim Nilles-Pelosi. So we are very happy to be here in the company of two of these authors of this fundamental paper in this field. So it's clear that I have to focus on this actually. But in fact, I think it is the most promising one anyway. So B and C are inflation, there's many fields. C is axiom monodromy. Also interesting suggestion. One of the proponents again is a very good friend of mine, but I mean, it's still, I apologize to Alexander Henstra. I cannot discuss this. I will focus on A, and on a proposal derived from it, which I will call winding inflation. I will explain. So the first point is that it's clear that you can have a winding trajectory on a two-dimensional periodic field space. So let's assume I have not one axion, but two. Both axions have small f, and f determines their range. And so apparently you're limited, but of course, if you let your field roll over a long distance along such a winding trajectory, you can have effectively a large field inflation model in spite of f being small. Now, clearly, okay, I said that the trajectory can be long, but you need to realize a potential forcing you on this trajectory, which you can do through an interplay of appropriate multi-instanton effects. So we have cosines of various integers along this and this side, and things can be such that you realize such a valley. But this is not so easy, and so even getting this kind of effective Transplanckian axiom is difficult. And so here is a suggestion how one can get around this. So let's again start with two stringy axioms, both satisfying that f is smaller than 1 in Planck units. And these axioms are also moduli, the moduli of the string compactification. And if you have in your space so-called fluxes, field strengths of other higher form fields on the compact space, you can stabilize these moduli. And a judicious choice for stabilization allows one to stabilize exactly one linear combination of them, such that the remaining light field is forced on the axion trajectory. That's in fact very simple. You need to only give a mass to a certain linear combination of the two axioms, and in this linear combination, you need to include some large integer number, which is possible through flux trace. I will explain a little bit better in a moment. Then you also have cosines along both directions, with coefficients that you are able to maybe able to tune using exactly the features that Yvonne mentioned, because there are other moduli. Effectively here, these constants are related to other moduli, the Saxon in particular. And so what happens now is that you're exactly on this one trajectory in a flux-derived model. And now comes forgive me, one more technical slide. What you can concretely do, this scenario is fairly concretely realizable if you go to a situation when you use complex structure moduli of the type 2B oriented code. I call them Z1 to Zn and UV. I distinguish those two. I go to what is called the large complex structure limit, when the imaginary part of those moduli, the saxions, are large. And in that limit, it turns out that the Kähler potential depends only on the combination U minus U bar or V minus V bar of these fields. So basically, the axionic part of that complex scalar drops out. It only arises in exponentially suppressed subleading terms. And the same is true for superpotential. In the superpotential, through a flux choice, you have precisely the freedom you need to give this combination U minus NV a mass. And without these exponential terms, it is clear that W leaves one of the originally shift symmetric directions, real part of U, real part of V flat. And if N is much bigger than unity, this direction is closely aligned with real part of U. So it's exactly the KNP idea realized in a way which is, however, different than just by combination of cosine potentials. So now the exponential terms induce a long-range cosine potential for this field. And so what one gets is a very peculiar picture. One gets the potential for a field which has apparently a long range, but you see both wiggles. You see the long range wiggle coming from one axiom and the short range wiggle coming from the other. And if you can tune the coefficients of the cosine terms appropriately, you can, in spite of those wiggles, realize low roll inflation. And very intriguingly, this in fact realizes a loophole in the regularization conjecture argument against axionic inflation, which has been noted at about the same time as this model we studied before by Rodelius and Brown and company. And it is the following. There are here two instantons involved, which you see through two different cosines. It's like two different charged particles. So one of them is the sub-Planckian instanton. It is the one which has this long range. And this is, sorry, the sub-Planckian instanton is the one that is the short range. Sub-Planckian means F being small. This is the one maintains regularization conjecture, because you need such an instanton. And the other one, the blue one here, is a super-Planckian instanton, which realizes inflation. And so together you get both inflation and some weaker form of regularization conjecture. People call it the mild form. The mild form means that not all particles satisfy this conjecture, but there has to be at least one particle satisfying the conjecture. So apologies, let me see what I, this is again a good point to interrupt for questions. I mean, this was a little bit maybe fast, and for the insiders, it will become simpler again. I will jump levels, okay, between stringy detailed stuff and introductory stuff. So here's a point for the experts to ask, who don't understand or maybe have criticism or comments.
I have a question.
Yes.
So what controls the relative size of the amplitude? So can you make it in a controllable way that the wiggles are small compared? In
principle, yes. Controlled, as you see in these pictures here, the exponential part. So if this V has a certain imaginary part, which is the subtheorem, then this is what controls it. So the I times imaginary part of the V gives you exponential suppression. And so the stabilization of the saxions, which you can in principle govern in precisely the famous complex structure landscape. So this is a model where really, if the complex structure landscape, as we were taught 20, 15 years ago exists, you can tune exactly those numbers. That's the hope of this type of model. And I'm jumping now ahead. More recently, there has been a paper, where is that? I will comment later by Carter et al., who claim, I mean, these prefactors also depend on some integers, the so-called Gopal-Kumar-Vafa invariants, and those can be hierarchical. So there has been an attempt recently to realize this without tuning, but directly by the choice of the right model. Which of course then is limited. I mean, tuning, maybe you can go huge numbers, this maybe up to 100, I don't know. But there are surprisingly large examples. More questions, comments?
Yeah, no, I just wanted to ask if you go, so you say, so this seems, and I think it's related to Marco's question, it does depend on your choice of little m and big M, which are just constants that you don't know, that will depend on the stabilization of everything else. Is that correct?
Yes, precisely. These are not constants, but there are other moduli, moduli which do not enjoy a shift symmetry. So they get stabilized once you switch on flux in general, I mean, all of them. And then you have to be lucky to get the right point.
Right.
And of course, people who, I mean, I like that very much, this idea, of course. I mean, we worked on this and it looks promising. And other people are skeptical because, you know, they tell us you need to find the model, but you know how hard it is in the landscape to really find the model. You know, there's this calculability issue, finding a point in a high dimensional lattice.
Yeah. So, but like maybe a toy model where you can see the rough to get an idea of what kind of values you need and whether they are realizable or not?
Yeah, you should read. I mean, I have written 3 papers on this. I do not want to tell them too much here. I mean, we looked in great detail as far as we could. And as I commented, the paper Westphal looks in more detail. And then there's recently, so in fact, the idea is related. So maybe you want to look at those papers to recent work on getting small W0 in the context of.
Oh yeah, I read those. Yeah, I was wondering.
So this is the type of thing you need to do. Okay? It's actually pretty much the same technology.
Right.
Used in different contexts.
Yeah. Okay.
So people who do heavy computer code with Calabi-Yaos and fluxes can, in principle, make progress here. I am not that kind of person, and I have not tried hard, I must admit. But I'm optimistic.
Okay.
Cautious.
Yeah. Thanks.
Good. By the way, so what time? I'm about 30 minutes in time, right? Gone. 35. Is that right?
Yes. Yes.
Good. Okay, so I want to sell one more point, a structural point about the winding inflation models I just described, which is interesting in the context of gravity more generally. So the structural point is the following. How does gauging Higgsing works? It was also a point which is relevant to simply gravity. So let's have a fresh start. For everybody can follow. Everybody who doesn't care about string theory can follow. Here, the first line is a trivial line. It's a p-form gauge theory. I have fp+1 field strength squared. Fp+1 is dap. Everybody can follow. Here, I write the same thing with 1 form degree lower. The p-form field strength fp is dap minus 1. Now, I can combine these 2 theories, and I call this Higgsing for reasons that will become clear in a moment in the following way. I can simply write down both kinetic terms together, but to the kinetic term of fp, I add ap. You see the form degrees match. I can do that. This is well known and claimed to be Higgsing or gauging of one p-form theory by the other. Now, this has a special case. The special case is p equals 1, such that p minus 1 is 0. In this case, you have f2 squared here, and here you have f1 squared, but f1 is d phi, and you add a1. And now you see in this case, it's what people usually call Higgsing. Here I simply made a scalar together with a vector, both massive, by combining them in a Stippelberg way. Okay. Good, so this was my mini reminder of how Higgsing generalizes to higher p-forms. Now you go to a special case, a kind of sick case, apparently sick case, -1 forms. So p minus 1 means that L minus 1 is integral over f0 squared. So this is kind of, you would say, what kind of gauge theory is this? I mean, there is obviously now no real, you cannot write an a-1 form, but there's still flux quantization. So you have a discretum of vacuum on a parabola. And the dynamics of this is as a discrete set of vacuum associated with the main walls, which can fluctuate. So in fact, you can dualize the theory, then it becomes slightly less sick. You go star f0 is f4, f4 is dA3. This coupled to the main walls is a proper gauge theory, a gauge theory which kind of is a little bit on the sick side. But it exists. I mean, theory of fluctuating the main walls. Now, crucially, one can now use this theory to Higgs a 0 form. In other words, an axiom. And the Lagrangian is written down here by exactly the scheme before. You have f1 squared and then f0 plus a0 squared. A0 is the axiom, so I rewrite it. It's d phi squared plus f0 plus phi squared. F0 takes discrete values. People who know realize this is the axiomology. This is how you give an axiom a mass without breaking its gauge invariance. People who don't know have learned what axiomology is in one line. Okay, important point, questions are welcome. Also, questions by people who are not expert in the field. Famously associated to the names of Dvali and Kalapazorbo, and actually there are some people before and after discussing it, of course. People call it Kalapazorbo mechanism, although Dvali actually has the first paper, I think. Good. So now what happens here, so basically I recall this Lagrangian, and this is of course just the gauge theory perspective and axiomology. I said that. So turning on fluxes, the thing I described before in winding inflation is exactly this. This combination, this U minus ND, which I described and argued gives you a nice K and P type model is precisely this. So phi x is one axiom, phi y is the other axiom. You have this combination of the two kinetic terms, and then you make heavy a certain linear combination. And this is a flux number, in other words, the particular gauging. It's like having two vectors and making a certain linear combination of them heavy by Higgson. And then you get precisely this trajectory, so it's a very nice, I think, theoretical way of understanding what happens. Okay, I said that already. Same Lagrangian formula here. I'm late a little bit. Good. As an aside, which was a very important aside, of course you can do the same thing with two forms. One two form, the other two form. The Higgson term, d phi plus ax plus nay. So you here exactly, as I said, make one linear combination of gauge fields heavy by one Higgs field. And you can now calculate, I won't do that, what the gauge coupling of the resulting light, single light gauge field will be, and it will be lowered by a factor 1 over n squared. So this is a way through Higgson to break in effective theory the gravity conjecture. This is an important point. So both in the axion case and in the vector case, you can do it. So far, there's not a believable stringy implementation like the binding proposal in the one-form case. So it appears that the zero-form case works, the one-form case not so clear, but the theoretic idea is there. And so if a model can be found, then one can maybe iterate this. So one can, combine two vectors in one by Higgsing, and then this one with another one by Higgsing, and so on. Then the effect exponentiates. The exponentiation of this mechanism is called clockwork mechanism. And that allows you, in principle, to break the gravity conjecture exponentially strongly. So in field theory, you would actually not believe that something like the gravity conjecture can hold. It's not clear whether field theory wins, field theoretic model building, or the stringy or quantum gravity statement, it cannot be broken. Good point for a break, for a question break, short question break. Anybody has a comment or question? Now I'm already pretty deep in recent critical swampland, pro contra swampland discussions here. It's not so clear what will give.
Could I ask a question? So you are saying that doing this trick for a gauge theory, U1 gauge theory, which you did with the axion, might not work in the gauge field case. So.
I have no stringy example. For the axion case, I told you with the complex structure fields how I imagine it could be realized. You could still say we won't find the right model, but in principle, I have the right cycles, the fluxes. I can argue that it can be done.
Yeah, because in some way, I think this question that there are no global symmetries is a very strong criterion, which I think many people believe more than the weak axion conjecture in some way.
But so, I won't, Hans-Peter, but look, by what I'm doing here, I will not violate this, because even though I can maybe exponentially strongly lower the scale of the gauge coupling, I cannot lower it to 0. I cannot also take the limit, because it's all in integers and fluxes. So if somebody could provide a stringy realization based on finitely many cycles and flux choices, you would not violate the global symmetry conjecture.
Or you would say that n should be finite in any case.
N should be, I believe, I think everybody believes the string landscape is finite. But recently there has to even be a proof in the type 2B constant by Thomas Grimm. I will not discuss this. In another interesting paper I will not discuss. We cannot, given the Calabi-Yau set is finite, tadpoles are finite, it looks as if the landscape is really finite. Has been conjectured for a long time, but there has been progress recently. So finite but very small number does not violate the global symmetry conjecture.
Yeah, no. I just was here asking the question whether you see a difference, let's say, between the axion case and the U1 case. So you just say you don't have a string model. If you would find a string model, you would put it on the same level, but conceptually it's still at the same level.
Yes, I have neither found a model nor have I found a conceptual reason why it could not be implemented. Okay. Maybe there is no model, and there's a conceptual reason why one forms really, as you suggest, are different than zero forms. It's quite possible. Or maybe, to be very brave in your presence, maybe KNP will not work in the end. It cannot be done. Could also be. We have no concrete model yet. Of course, we don't hope that, because I like KNP and I like large field inflation and axions and so on. But either way, could any of these possibilities could be realized.
Thank you.
Good. I have this interplay of cosines can also be realized can also be maybe used to realize a small uplift. By interplaying cosines, you can have such a little uplift here. There's a recent paper I wrote. I will not try not to use this stage to selling this too much. I already talked about Gupo-Waffer invariance. Let me skip that. My mini summary of the first third, maybe already first half, is I think some of the simplest string inflation models are of the type of interplay of several cosine terms. This could be KNP or winding or some modest range monodromy or some mix of those. And I cited here only 2 papers of many. Something like this could be our influton. This is something I could imagine being realized and fine-tuned in string. First third over. Maybe break now or break later?
Up to you.
Okay.
So, sorry, maybe I can come back.
Yes, yeah, please.
Point. I think my question was different when I talk about this axiom. So suppose now, so my question is the following. Suppose now I want to, for some reasons, I have a model where the axiom and the axiom, both of them evolve during inflation. So you may say, well, I cannot, but the axiom is the one that is mostly inflating. And now the question is, can you say that, can you use this version of the weak gravity conjecture to constrain the range? Because now the decay constant is not a constant, but both of them are moving, the axiom and this axiom.
There have been interesting work on this subject, but I forgot now the details. Parametrically, things are still as they are in the gravity conjecture. I mean, the axion direction is finite, limited, and the axion direction can take you to infinity, but if you go to infinity, the cutoff comes down. A subject I will mention later. At the moment, let's just accept this. So the cutoff comes down, so then you cannot go to infinity. So then, in principle, you cannot have parametrically large field inflation by combining these 2 things. However, since you are in practice only need a few you don't need parametrically large field inflation, given the present data. So, of course, a little bit motion in the axion in parallel to the axion can help, as can a KNP or winding type model, even with a factor of 10, can help. So I don't think I have a good theory answer. Unfortunately, the clean theory does not match well on the phenomenology of inflation here. That's my problem. That's the point. You see.
Yeah. So, but if I forget about inflation for a moment and I just want to answer the question, which constraint will I have if just from the pure no inflation? I just want to see whether this decay constant, which is not constant anymore, if there's a relation between the instant on action and all this.
I think you simply have to use the decay constant, and the suction at any given moment in the dynamical evolution tells you what the suppression of the instantons is. So there's nothing surprising here.
So you'll say at any time.
Yes. I think we have to use the constraint at every given time in suction evolution if it evolves.
Yeah. Okay. Yeah.
Good. So then I suggest the following. I will move on a little bit, and we will have a break in the middle of the second part. I think I'm losing too much. It's good to have lots of interruptions. Please continue asking me. But let me move a little bit more. Okay. Namely, let me come let me completely change subjects now. Not completely, but strongly. De Sitter. So one plausible sample conjecture, which I did not put up together with the first three because I don't believe in it so strongly. It doesn't have so much theoretical support, but it is very much more important phenomenologically. It's the conjecture against De Sitter. People say, okay, cosmological constant, negative simply cannot be realized. Sorry, cosmological constant is always negative. Positive cannot be realized. Not even for a finite amount of time, not even as a metastable vacuum. So this reflects a long-standing unease about the status of the Sitter space in string theory and contragravity. So many people have tried to give arguments in various degrees of strength and very different logics against the Sitter. The Sitter is a complicated object if one thinks about it carefully. So more recently, this has found concrete formulations of varying, in context of the swampland program, concrete formulations of varying strengths, I should say. For example, the strongest one was the famous V prime or V conjecture. So potentials have always to be steep, and then it turned out to be too steep, and people have, too strong, people have corrected by adding this conjecture. This is together is kind of a conjecture against slow roll. So you cannot say all potentials are steep, but all potentials forbid slow roll or cannot realize slow roll. And this is, of course, very, very strong statements, not only against inflation, but against our present universe, because it appears that we see cosmological constant. Not definitely, I mean, could be quintessence, but even if quintessence, it's a fairly flat potential. So let me advertise here at this point that some people of us have committed, even in the sense of writing a book on the opposite side of view. You know, this is the whole paradigm, naturalness, string landscape, multiverse, all that collapses or could collapse if the previous statements are true. And so the question is not only do we want to give up the paradigm, but do we have a good alternative? And so clearly you understand that I'm very worried by this and also very interested, and I'm trying to understand. And you will see that I'm not only working on the side of what I hope, namely pro-multiverse, but also on the opposite side, because our recent paper I will advertise later actually suggests a stronger argument than given before against KKLT. Good. So let me maybe before the break give the fundamental argument pro these conjectures of Guri, Barfa, and company. Okay. So why is realizing the Sitter so difficult? This is again now very simple level. You know, you don't have to know anything, just for everybody, including non-string theorists. So let's look at the generic compactification with some volume, volume V. Let's put some positive energy source in the compact space so we can hope to uplift or to live in the Sitter. What will the Lagrangian in 4 dimensions be? You get the ancient Hilbert term simply by integrating the high-dimensional gravity Lagrangian over the compact space. So prefactor will be volume. Then you have to trust me on that. The metric will give you some kind of kinetic term for the volume. The volume itself is a metric field, it's a modulus, it's dynamical, and it will have this logarithmic type derivative. And then here I added a positive energy source to make a decision. So now I want to analyze this after value scaling such that my metric field, the volume, is canonical. The transformation is given here. Phi is log volume. 2-line calculation shows you that what you get is 4D gravity in the Einstein frame, kinetic term for the modulus field, not an axion now, okay, modulus, volume modulus, canonical. And now, due to this structure here, the prefactor of the volume, you get energy times e to the minus v. So unavoidably, in the limit that the volume gets decompactified, large, the energy goes down in Planck units. So you get this runaway. You do indeed always get these deep potentials, these V prime over V order 1. Whoever has doubts or questions, please ask now. It's an important point, okay? So naively, you really think, oh, look, there is a good reason that the Sitter is difficult. Runaway is natural.
Sorry, I don't understand this point. An exponential cancels out in the derivative over V. No? If you take a derivative with respect to some field inside E, then everything gets small in the lower spline.
So here, this potential is e to the minus v, yes.
I mean, some field inside capital E. E is not just a constant, right? There's some structure, some potential with some other capital phi, chi, whatever you want to call it, field.
No. E is a constant here.
That's a constant. Okay.
Respect to phi is a constant. So what I'm doing is I take a compact space and I add at some point in the space some positive energy density, say an antibrane, something, or I have some local model which has a non-zero F term. The point is, if you take the volume of the whole space to infinity, then that positive energy contribution goes to 0 in Planck units.
Just an argument that this phi field, little phi there, is not an inflaton. So what? It's not the only scalar field around, right?
I gave a toy model example. The point is that if you people who analyze in single field, so for all single field directions in which you do that, you always find this behavior. It is not so easy to find. Put differently. There's always some direction which is hard to stabilize, like here's a volume in which you see this runaway. You need to make sure that there's no direction in which you can run away and thereby lower this energy. Let me go on. You will see that I'm trying to answer exactly your question in the next slide, okay? Is it Manuel, right? It's Manuel, right? Who's asking? Sorry, I can't see all the people. Manuel.
Yeah, it was me. It's okay, go on.
I want to go one more slide, okay? Then you can ask again. Good. So here, now I combine two such runaway potentials with different signs. Then I can in principle create ADS, right? I mean, these effects can be various such effects. So if you combine two such falling potentials, I can create a minimum or I can create a maximum, but I cannot create a minimum of 0. I need at least 3 different such runaway behaviors to get a minimum at above 0. So it doesn't tell me that it's impossible. It tells me that given the generic feature that I explained before about moduli and how moduli interact with the energy, you need a certain minimal degree of complexity of your model to realize such a scenario, a minimum above 0. And this is what triggered people to be skeptical and what makes it hard to construct a fully explicit model in a simple string setting. So it's exactly as Manuel suggested, you then involve more fields, you stabilize some of them, you hope that the energy does not depend on some field which can run away, and then you can maybe do it. But the simplest models don't work. Manuel, can you comment again?
Fine, yeah.
I'm not saying it cannot be done. I'm just saying what complexity is needed to do it. So there's some tuning of fluxes, accidentally small and large parameters can be realized, which allow you to have this interplay here. So this, in fact, requires the tuning of these various numbers, of the various contributions to the potential. All of them may be decaying, but together they give the minimum, and you can accidentally tune. And the first such scenario was KKLT, and the second one was large volume scenario. And they claim to realize exactly this interplay of various such simple terms to give you a minimum above 0. And so I will now recall so the plan would be to recall how KKLT works and discuss recent criticism, and which was historically important to trigger the above debate. And then I will come to a rather different concern, which is the moment to me appears to threaten KKLT more seriously. I will explain that in a moment. I'm still, now it's an hour, right? I cannot see the watch. Is it 11?
Yeah, it is.
Okay. Shall we have a break now? Maybe 10 minutes? What do you think?
That's very good, yes. So maybe we can resume at 11:15. So this will be 12 minutes break.
Okay. I'm happy to stick around. I want to, what is the time? 11:15. Okay, it's 10 minutes. I want to have a coffee, so I have to excuse myself for 2 minutes to get a coffee. But I'm happy otherwise to stay online and have discussions. So everybody who has further questions to what I just was saying, please ask. Maybe you should switch off the recording for that.
Yes, perfect.
Perfect. Okay, good. All right. So the next few slides will be a bit stringy. But again, I ask your forgiveness for those who are not string theorists, and I will also have a more general final part of the talk. So before we discuss the problems of, so I told you about the general problems of de Sitter. And I told you there are proposals which claim to beat those general problems. And let's discuss maybe the simplest one, KKLT. So let's take a Calabi-Yau with all complex structure or shape moduli fixed by fluxes. I will not explain how in detail this is done. We just ignore them and leave only one field, the Kähler modulus T, which has a real part, which is the volume, or the volume to the power 2/3, and an imaginary part, which is an axiom, which in this case will not be important for me. The Kähler potential is this one. The superpotential, due to these fluxes that I mentioned, is constant. Together, miraculously, these things conspire to give you an exactly flat scalar potential. So this is called a no-scale mechanism. Many know it. For those who don't, just accept that the supergravity formula gives you exactly flat potential based on this particular ingredient, these particular ingredients. Then the next ingredient is that there are some branes with gauge series, and there's gaugino condensation on this D7 brane stack, for example. And that adds to this constant and term e to the minus t. The exponential now is not an instanton as I was before, but it's just a deep infrared, basically something like gluon condensation in a SUSY form. So again, I'm very happy that I'm able to mention our host, Hans-Peter, here in this context. For the fundamental understanding of these effects many years ago, in fact, in the heterotic context, which I will not discuss. Then the third ingredient, remember I needed 3 ingredients at least, was the anti-D3 brane, which allows me to uplift. This has to be placed in a warped throat, which is a certain region of the Calabi-Yau with strong so-called warping, where all scales are redshifted a lot, such that this uplift is not too strong. So this will give me a certain positive energy contribution with the decay, exponential decay that Manuel Drees that we discussed briefly with Manuel Drees before. So now the picture is the following one. Leading order, we have just this 0 on the axis. The gaugino condensation gives you this minimum here. 2 terms arise because of a quadratic and linear term in this effect, which is part of supergravity. And then the uplift under D3 lifts you here to this point. And for example, to 0, but could also be a little bit above 0, could describe our real universe. And there's been many, many long-standing criticism and critical debates of this issue, in particular the anti-brane, which I think this part has remained plausible that the anti-brane can live there and uplift. So there has been criticism, but I think it has not been borne out. Actually, let me see. Yeah, sorry, now I reinstated my red dot. So, okay, good. Right, so now there's recently been criticism rooted in a possibly too simplistic treatment of this D7 gaugino condensation bulk coupling, which is a complicated story, interaction of the free-form flux with the gaugino condensate. And this, even though I'm kind of very proud of that work that we did together here with, let me cite the paper at least, with Hamada, Shiu, and Sulea, in the end, I think it goes out pro KKLT. And so I will not discuss it, simply for time reasons. Okay, apologies. I skip some important slides here, including very interesting work by other people here. Gerben Denken is a postdoc in Heidelberg now. Let me just nevertheless jump it. If there are questions, we can discuss later. I want to advertise or discuss a new concern, which starts with a so-called throat gluon problem, which is not by us, which is by Carter, Moritz, and Westphal, and from which we think we made a kind of almost killer argument for KKLT, at least for the controlled regimes that was discussed so far. Let me start with what we call the throat gluing problem. So KKLT has this ADS potential with the depth e to the minus real part of t. This is kind of e to the minus some power of the volume. You remember, this is a minimum that we start with. And it has an uplift, and the uplift is also exponentially small, and this is governed by some ratio of fluxes. K and M are flux numbers on 2-3 cycles in the Klebanov-Strasser throat, this is the strongly warped region, drawn here pictorially like that. You cannot uplift too much or too little. You need to uplift the right amount. These 2 terms have to match to give you a Minkowski or stable de Sitter vacuum, metastable de Sitter vacuum. That leads to a certain condition between the real part of T, the volume modulus, and two flux numbers that govern the Calabi-Yau, basically the warped region of the Calabi-Yau. Now, at the same time, the throat carries a certain amount of charge. So this throat here, these two numbers, they also determine together its D3 charge. It's like an electric charge sitting on that throat. And so together, you get the condition that these two numbers, these two flux numbers give you the charge N, and this charge N determines the radius of that throat. Sorry for, it is that complex. I was not finding a way to make it simpler. So now what happens is, most naively, you need the Calabi-Yau, this radius here, to be bigger than the throat. I mean, how can you glue in a small throat, a large throat and large Calabi-Yau? So you think this is a big Calabi-Yau, there's a small throat glued in, we have an inequality here. This inequality leads to a problematic inequality between flux numbers. There's on the one side, GSN, which governs the size of the throat, and on the other side, K over M from the flux numbers. You can now translate this using that this K is N over M. You plug it in here. The N drops out. You get this inequality. You get this 1 over G squared M squared, 1 over GSM squared has to be bigger than unity. And M is, roughly speaking, the flux living on that cycle, keeping the cycle open, keeping it from shrinking. It's simple algebra, but unfortunately 3 steps to get to this inequality. Now what happens next is that you discover that GSM has to be bigger than unity for reasons of supergravity control, and the number M itself has to be bigger than 12 for metastability of the antidecerebrate. So basically, this Calabi-Yau in that region should not be too singular. That makes it impossible to make this number here, GSM squared, small. This is parametrically a large number, reasonably large, I mean like 10 or 12 or 20. But it's still bad because 1 over 20 is not bigger than order 1. So as a result, you cannot really have the picture of gluing a small throat into a large Calabi-Yau. So this itself is not obviously a problem, however. It simply means that geometric intuition fails. So let me explain more detail. The metric on the Calabi-Yau is a 10D metric here. There is a prefactor for the 4D space and the Calabi-Yau metric G twiddle, and then there's a warp factor. A function h of y is a parameter of the Calabi-Yau, which appears here and here together. This is a slightly more general compactification than just a product compactification of Minkowski and Calabi-Yau, but this is still perfectly consistent with 4D Poincare. It's a very well-known story. This warp factor is the thing that allows me to talk about the throat. This is what governs this region, what makes this region special. You know that there's a very low redshift here, and the anti-D3 brain can sit here. This is the Calabi-Yau, this is the throat. What I've been showing so far, the throat gluing problem is that this picture here cannot be realized. It's more like that. You have to glue a large throat into a small Calabi-Yau. That looks odd. The warp factor changes along this direction. Here you have large warping. This means that here the redshift is big, the anti-D3 brain uplift is small. It all fits together mathematically, and looking strange is in principle not a problem. So at that point, I think things are still undecided. Carter et al. Have seen an issue. It's not clear if the KKT dies of this issue. And now I will try to tell you that there is a singular bulk problem which makes this issue potentially deadly. So the actual problem is not that the geometry defies our standard intuition. It is that the Calabi-Yau may be forced into a singular regime where the warp factor h is smaller than 0. Now let me remind you that the warp factor h being smaller than 0 is a very bad thing. It means that the metric becomes imaginary. It's not something you can really sensibly talk about. So, and the danger of gross singularity, as this h is taken small, has already been mentioned, in fact, by an appendix by Carter, but they didn't turn it into a quantitative problem for KQLT. Because this is actually non-trivial. I mean, it's not clear that you arrive at the problem. I will now briefly, very briefly, try to explain. So one needs to want to demonstrate that generically, the regime of KQLT works enforces that the warp factor is smaller than 0 in a large portion of the Calabi-Yau geometry. For this, I have first to understand or explain why, whether and how H behaves, this warp factor behaves near sources, near brain-like sources. So for example, if you have a D3 brain, near the D3 brain, the warp factor goes up. This is exactly like the throat that I mentioned. I mean, this is strong warping. Basically, if something wants to fall, if something can fall, it falls into that direction. It's like falling into a black hole. This is the famous setting of ADS CFT, where you have this ADS 5 times S5 throat. This is just a kind of a simpler version of that. Oppositely, by the O3 plane, the object with the opposite charge registry, the warp factor goes negative. So this problem arises actually always when you have a typical string classification with brains. However, that's not a problem, because in that region, we are here at stringy distance from the O3, and we don't have to trust the supergravity approximation with the metric. We trust string theory. There's a resolution of that region in string theory, which we take more seriously than kind of 10D Einstein equations. And so such small singular regions are okay and are always present, in fact. Now the bulk singularity problem arises from the macroscopic behavior of H. So it turns out that H is forced to go negative over a large portion of the space. And the way one can argue that the way we argue this is that you need to look at the size of the warped D7 brain cycle, where the Regina condensate happens. So this cycle, I told you before, the size here is governed by n over GSM squared. So I translate this into the volume of the cycle. This is just a rewriting. This is the volume. There's a GS going here, then this becomes the volume in string units. This volume, the actual physical volume of the cycle, which also governs the gauge coupling, in fact, is the integral of the Calabi-Yau metric times warp factor. So if I extract the Calabi-Yau volume, it's just the averaging of the warp factor over the cycle. Now, without loss of generality, I can use the Calabi-Yau such that I can use the Calabi-Yau metric such that the volume of the Calabi-Yau is order 1 by normalization, and then the cycle is also order 1. So this is just a convention to make things simpler. So in effect, what we are doing is we are constraining the warp factor on this submanifold sigma. And the warp factor, by this logic, here the size of the cycle, here the relation to the warp factor is given here. The average of the warp factor is this number in terms of certain fluxes on the Calabi-Yau. Now, we have, for a large part of the D7 volume, we have that H has to be smaller than n over n squared. Otherwise, the average value could not be this. At the same time, we know how this warp factor behaves. It solves an electrostatic potential type equation. It solves this type of Poisson equation. And this type of Poisson equation has on the right-hand side a large source. There are GS units of positive charge localized at the conifold. This is the big throat that we need for the anti-disturbance. And then there have to be minus GSM units of negative charge scattered in the Calabi-Yau. So this side here, so it's an electrostatic problem on the Calabi-Yau, which is scaled up to a large size. And so what I now have is that if the number GSM would be order 1, we would have an order 1 solution to a Poisson equation. But in our case, this number is large. So H is scaled up, at the same time it's bounded below a certain number on the D7 brain. So putting that together, these two together tells you that the ratio of the derivative of H relative to H has to be large. It has to be a quickly changing function in this mathematically precise sense. And then one can Taylor expand around a certain point y0 of the D7 and see that the thing simply has to run negative near the D7. it's mathematically, in a generic case at least, unavoidable that this electrostatic type potential runs negative in a large part of the Calabi-Yau, namely near every point of the D7 brane on which the Gaussian component Z helps. So basically, that was probably too technical for everybody except those who know this field. Let me now repeat in pictures. The situation you want is the Calabi-Yau, which is smooth. There's some D7 brane, and there's sometimes these O planes where you have this negative regions with warp factor, which resolve in string theory, which you don't worry about. The KKLT regime drives you in a situation when these singular regions merge and you lose control completely over a large fraction of the original Calabi-Yau. Then basically nothing you did, at least not in supergravity, in 10 supergravity, is trustworthy anymore. And you cannot avoid being forced in that regime. And now, let me put another picture. So you know this warp factor, it goes negative near the branes. It sometimes has poles here. But the problem is not that. The problem is that even the average factor goes negative, which cannot be avoided. It's like having an electrostatic potential in a plasma. In a plasma, of course, you know that near the electrons, the potential always diverges. Still, you can have a sensible average potential. But this average potential is driven negative, and then the metric becomes singular in that regime. And even though the logic is all simple algebra, I am aware that this could not be understood from what I just said before. I mean, you could only see the rough ideas, but it's just an issue of combining an unfortunately large set of 3 or 4 constraints together. There are, of course, possible escape routes, which we discuss in our papers, but they amount to special arrangement of branes, which you know you can't, which you don't know you can't do. Large H11, large number of branes, some stringy miracles, which you can hope for. It's not clear that these escape routes lead to a result. It's not clear that KKT doesn't work, by the way, but it's not clear either that you can put this in a control regime. That's an open issue. There's an interesting recent suggestion by Cutter and Moritz, that in the case that the negative D3 plane effects, D3 tadpole effects reside on curved D7 brane states. So I explained only how you can get these negative regions near O3 planes, which is, I think, the simpler case, but they can also arise near D7 branes. So you can introduce a negative charge on D7 branes. And in that case, they propose that the corresponding singularities are resolved in an F-theoretic way by the splitting into several branes of different types. So you have to deform your stack of the 7 branes in a non-trivial F-theoretic way, and then you gain control, smooth control, of the singular geometry. However, you cannot escape the fact that the region remains strongly curved, very far away from a standard Calabi-Yau. So the problem that remains are strongly curved regions, and hence at present no quantitative control of the KKLT scalar potential. In other words, you still don't know whether it will work, at least in my understanding. Before I summarize, maybe, yeah, I don't dare to ask because I said a lot of confusing things. The talk will become much simpler from now on again, but let me maybe pause here whether anybody has an issue, could at least ask a question about the general setting here. It's a rather involved story. So the questions about the throat gluing or singular bulk problem. The paper yeah, Yvonne.
Yeah, sorry, maybe this is a very stupid question, but maybe I missed why is the warp factor negative? So in some slides you argue, yeah, I don't know how many slides back. So the, yeah, not the next ones. In the next one where you, yeah, when you argue why it becomes negative, your argument?
My argument is that I can constrain the average value of the warp factor given here on the D7 brane. This sigma is a D7 brane cycle, okay? And I know that this number cannot be too large. because the cycle is something I calculate. It's the Gaussian condensate. You know, it's constrained in the Calabi-Yau how large the cycle is. And large includes the warp factor. Accepted? Okay?
Yep.
Second point, the warp factor as such is a solution to a Poisson equation on the Calabi-Yau.
Yeah.
This Poisson equation is not a single charge equation, not like a sphere and one plus and one minus charge. It's a sphere with like factor n or NGS enhanced charge at one point and the opposite at the other region somehow. So you have a function, an order 1 function scaled up by a large number. That makes an order 1 function like that a steep function. And you know it's parametrically a small value near a certain cycle, which is the Calabi-Yau. So then you know it has to drive negative.
Okay.
Basically, you simply take a function which has small negative region, and you are forced to make it. You are forced to make the average value here on this cycle small. Then you push the full function down by a constant, and then it runs negative in a large region. Maybe I put again in pictures. If you have a curve like that, the function is small here and steep, then you know it runs negative nearby.
Okay.
So it's a combination of me knowing that the function is a standard order 1 function, solution of the Poisson equation, with plus and minus regions, okay? But this function is scaled up by a lot. And then in a certain point, which I have no choice, I cannot choose where it is, at a certain point, it has to have a small average number, extended over a large region. Then it is forced to run negative nearby.
Okay. Okay, thanks.
I have another question.
Yes.
Probably a stupid question. So in all this calculation you've shown us, the string coupling GS plays a role.
Yes.
Is it possible that some, I don't know, very small coupling or very large coupling?
No, a very good question. We thought carefully. We formulated all the constraints in quantities like GSN or GSM squared or something like that. So the paper is basically about carefully doing that job. There's no escape route due to small GS. Of course, we tried parametrically to play with all the numbers available, and simply the equations are such that you can formulate the constraints in quantities excluding GS, basically.
Okay.
So it's something I cannot answer now. It's like 5 equations you have to carefully. I mean, it took us weeks to understand that there's no escape route there.
Yeah.
And probably because we are stupid, but I mean, it's still it's not like, you know, I don't think you can just look at it and see why it is impossible.
Yeah.
But I'm convinced it is impossible. Okay. There are more parameters I mentioned. You can roughly speaking, you can play with my maybe unsatisfactory answer to Yvonne. You can say, okay, but there may be a special function which, in spite of being large everywhere, still has an extended small region and doesn't run negative. This question can be posed, and we try to argue that this does not happen in the paper carefully. But special arrangements of these 3 and 3 could still do it. And then there's another tool which I didn't mention, the number of NC, the number of colors of the brain stack. If you go to large NC and complicated Calabi-Yau geometry, there's a possible escape route there. Looks very contrived, but it's mathematically possible.
Okay.
And then there's a claim by Carter et al. Who say, okay, we show how proper string theory will still resolve that negative region. And that, of course, I completely trust. I mean, the negative region in string theory, nothing is ever inconsistent. You know, in the end, you get some geometry there. But then the geometry is strongly curved, and you cannot calculate the Kähler potential anymore on which everything rests. Yeah. But you can, of course, still hope that the Kähler potential that will come out will somehow not be too different from the no-scale type potential I started with, and then KKLT will still work. So we are not saying we killed KKLT. We are saying the naive assumption or the standard assumption that it can be moved to a controlled regime just by tuning W0. I think that appears to be not true according to our work. More questions? What's the time, by the way? Sorry, how many do I have? 20 more minutes or something?
Yes. 11:42.
Good. Let me briefly make a brief summary. So the sitter. So this establishing what is proven KKLT is a key goal. KKLT appears to survive the recent 10D line of attack, which I did not even discuss. It may fall victim to the what we call the bulk singularity problem or singular bulk problem. It's important for the whole landscape that the LBS does not suffer from this issue. The LBS has exponentially large volume, so this whole issue of singular bulk does not arise there, at least in our present understanding. So in parallel to disproving KKLT LBS in more detail, we should try to get string quintessence to work. That would be very important as an alternative. And all I can say about this here, let me only show the slide because I want to say that the best string quintessence model maybe involve one of the people I've seen here in the audience, Gianmassimo Tosinato. I don't know whether he is still there. We tried to study them further. We discovered that there's what we call an F-term problem, which roughly has to do with the fact that the SUSY breaking, which you logically need, is too high for the potentially negative potential which you have. So you are exceeding all possible negative potential sources. The SUSY breaking will destabilize you. And there is some further recent interesting work on this, but all in all, it seems that quintessence is at least as hard to realize due to very clear, conceptual issues as metastable, etc. So it seems to be that there could still be a way out, consistent with the sitter conjectures, but it's not at all clear how to realize it. Right, that's the end of the story. For me, that is the end of the de Sitter part. I will now talk briefly for the remaining time about global symmetries. I will start from scratch in simple terms. Questions, comments? Good. Okay. So new subject. The previous subjects were very cosmological. This I do not know yet how cosmological it will be. But I think it's an interesting general issue for the gravity and swampland, and so and maybe after all, cosmologically it can be important to know how weakly coupled things are, how close you can come to global symmetry, etc. So I think it is an interesting cosmological issue. So now let me start it again from scratch. So one swampland conjecture, in fact the first one historically and the first one I mentioned in the beginning, is that there are no global symmetries. So the first question I will ask, and that goes together to a comment somebody made, I forgot, was it Yvonne or someone else, I forgot. So is this even really a swampland conjecture? No, I think it was, sorry, I forgot. You will remember who made the comment. So one may claim that no global symmetries is not really a swampland conjecture. Indeed, consider an effective field theory with a global symmetry. So one that apparently should not be consistent. What will happen is that standard black hole evaporation physics will in fact induce the expected violation, even if in the effective field theory I have not introduced such an effect. And it's very well known how that happens. You take a black hole, you throw in a lot of U1 charges, global U1 charges, the black hole evaporates, the charge is gone. So the dynamics of the theory, including quantum gravity, appears to violate global symmetries, even if the EFT has no violation. So the EFT appears not to be constrained by this conjecture. If anybody is confused by that statement, it would be a good point to ask. I think it's an important statement.
So you're assuming that the black holes don't get charged?
The black hole gets charged, but nobody can see the charge from outside, right? So you take the black hole, you charge it with a global charge, as high as you want, and then you wait. The black hole evaporates, the charge is gone. Quantum gravity dynamics destroys the charge. So the Hamiltonian, if you wish, of the whole theory, destroys the charge. But your EFT has no operator. Your effective field theory does not need to possess an operator which violates the charge. which violates the global symmetry. That is a surprising thing.
Well, I'm somewhat confused because the EFT is a theory without gravity. So then you say, if I then consider gravity like black hole evaporation, it breaks the global symmetry. So from that point of view, I would argue this is the same situation as you have for swampland conjecture, which says that theory which might be consistent otherwise is inconsistent when I also consider gravity.
No, but the theory is not so. Okay. First of all, I would disagree about the first statement. I think the EFT is the low energy EFT of field theory, including the graviton and its recoupling to the ingredients. Why not? I mean, this is what you call an EFT. I think, including semi-classical quantum gravity. Okay, that's my EFT. This EFT has no operator, which violates the global symmetry.
Yeah, okay, then I understand this. I understand the swampland that once you consider gravity something, but in any case, good.
Yeah. So I would like to have an EFT, which I can say, look, this EFT is inconsistent because it has a global symmetry. But it doesn't seem to be obvious that this can be done. Okay. So now. There's a caveat to what I said. Of course, black hole evaporation, I've used the word standard black hole evaporation physics, is an overstatement. I mean, we don't understand that so well. And so an independent argument, and this is what I alluded to before as a proof of a Cromwell conjecture, was given in ADS. So this is due to Harlow-Oguri. I have no time to even start reviewing that proof. Maybe many of you have seen that famous picture by now. So they have an ADS space here inside the circle, the boundary. So inside this ball, the boundary is the CFT. The boundary is where the CFT lives. And the statement is that if you cut your CFT in patches, you can reconstruct only this part of the bulk. Roughly speaking, due to Ryuta Kayanagi and other people, I mean, like how you reconstruct fields, degrees of freedom in the bulk from the CFT side. And you never reach the center. And the authors here involve what they call splittability assumptions. They say in CFTs in general, again, not proven, but they say very convincing, you can always realize any symmetry operation as a product of operations in separate patches. Here, 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 and here. Together, you should be able to rotate a charge here in the middle by a phase. But you can't, because these patches, separately speaking, do not reconstruct the center. How strong the assumption of splittability is unclear to me. Some people to me tell me it is unclear. Other people say it is completely obvious that it's true. Proof does not exist. Moreover, this argument is purely mathematical. It's a kind of a formal mathematical proof. It does not apply to what my main interest here will be, namely approximate global symmetry. So I will try to argue and convince you that an interesting thing to consider are approximate global symmetries. A proper swampland conjecture should consider EFTs where a global symmetry is approximate and say that this approximate global symmetry cannot become arbitrarily precise or arbitrarily high quality. And such an argument is not included in this Harlow-Oguri paper, and it's not clear at all so far it exists. So approximate global symmetries are not forbidden, and to me, it is crucial to constrain their quality. In a sense, the low energy effective field theorist, I would say, has no other way to approach the issue. For low energy effective field theorists, it counts whether you can bound the minimal amount of violation that is necessary for the theory to be consistent. Okay, so again, our interest is in quantitative conjectures against approximate global symmetries, and one such approach is, of course, the weak gravity conjecture. So the weak gravity conjecture tells you that you have a gauge symmetry, this coupling G, global symmetry arises in the limit G to 0. You can try to take this limit, and the ideal claim of the weak gravity conjecture is that this coupling G is bounded from below by mass of a charged particle over Planck. And so you can't take this limit. Now that's the thing I explained in the beginning. Now, such a strong statement has not been proven. Still, let me, for the purpose of the talk, assume at the moment the regravity conjecture. And rigorous progress in this direction has only been made in the context of the black hole mass spectrum. So for very highly charged particles, people are still hoping to get a proof of the regravity conjecture, but nowhere strong enough for this kind of limiting argument. So we want to consider a second route for approaching exact global symmetries. So now I'm explaining some recent work with these authors. So I already explained, from gauge symmetry to global symmetry, G to 0. Another approach is you have a theory with an approximate global symmetry, and you go to a global symmetry by switching off the coefficients of all operators which violate it. So you have an approximate global symmetry, means you have a theory which would have a global symmetry if certain operators were missing. And I should be forbidden quantitatively to take the corresponding coefficients to 0. This second way of approaching global symmetry is fundamentally different from the first one. There's no light vector field involved here. Here, on the left-hand side, even if the coupling goes to 0, there's always a light vector around. Here, there is no light vector at all. It's really from approximate global symmetry to exact global symmetry. And I would argue that, in fact, the practically most useful way to think about a global symmetry is exactly this one. This is what particle physicists always do, right? B minus L in standard model, flavor symmetries, dark matter stability protected by some U1, flat axion potentials. These are all examples of approximate global symmetries where we as physicists are interested in how precise the global symmetry can become. So now let me be more precise about this. So we start with an effective field theory, not with a symmetry, but with some global group action on it. An approximate global symmetry to me is the following. It arises if all non-singlet operators are either irrelevant or have small coefficients, as is the case for B minus L in the standard model, for example. And our goal is to quantify the smallness. In other words, to limit the smallness from below, to tell you that global symmetries cannot become arbitrarily good. In fact, an interesting conjecture inspired by black hole physics in this direction appeared recently by Fichet and Saraswat. Let me simply state what they claim, or what their logic is. They say in a thermal plasma, which they consider just because they can, the black hole-induced violation effect, I mean the effect that arises because there could be black holes and the black holes could evaporate, this black hole-induced effect should not exceed the symmetry violating effect due to local operators. That, of course, bounds violating local operators from below and achieves exactly what I just proposed and should achieve. But it's basically a new conjecture, which comes from nowhere. And we want, in the next few slides, I will show you a derivation instead of a new conjecture, at least for a subclass of global symmetries. So let me start. Before I start, let me say that, in fact, we will not be able to achieve that. We will only be able to achieve it for an important, I think, subset of global symmetries, namely those which I call gauge-derived. So there is then the following classification, which I should start. What type of global symmetries can I have? I can have gauge-derived global symmetries. By this I mean the following. I start with a gauge U1, and I Higgs it using an axion, just making it heavy by Stückelberg, if you wish. Vector and axion become heavy. If there was a light charged particle, this light charged particle now sees an approximate global symmetry because it is still protected from decay, but the vector which you need to know that it was gauged is gone. This is how you can systematically construct, as an effective field series, very precise, very good approximate global symmetries. But there are two other types for which I will not be able to make a clean argument. Second is accidental. So space-time and gauge symmetries forbid all relevant and marginal non-singlet operators. That could simply happen. In the standard model, you know, B minus L is a good symmetry at the level of dimension 4, simply because it happens to be that you can't write down an operator invariant under gauge symmetries in Poincare. And the third case is fine-tuned. You can imagine something even more strange maybe, you have coefficients. All coefficients of the relevant and marginal non-singlet operators are small by landscape type tuning. So if you have a landscape, you have many EFTs, you can tune the coefficients, possibly. And then you can be in a regime when those happen to be small, for no good reason whatsoever. So my focus will be on the gauge-derived case, the one which I would call a systematic case, where you really construct an approximate global symmetry. Good. So let me give you the minimal setting, and at the same time, already the main idea. Marco, I think I'm running out of time.
Well, you can take 10 minutes if you need, no problem.
I think I will finish with roughly this in 2 minutes. Okay, good.
Oh, that's good.
I promise not to go over time.
No problem.
I promise not to go over time.
No problem.
So I think I can make my point easily. So the minimum setting is the following. You have 1 over g squared s squared, just the u1. You have a scalar, a charged scalar with some mass. This scalar is charged on this u1. You see the covariant derivative here. And then you also make the gauge field heavy by Higgsing it with an axion. The axion is also there in addition. So now, if this mass of the charged scalar is smaller than GF, then what will happen is that the light field phi sees a surviving global symmetry. So roughly speaking, axion and gauge field become heavy, the scalar survives and the scalar is protected by something which is now in the EFT only global. Now, as already discussed, instantons break the continuous shift symmetry of the axion, which is hidden here and which is needed to write down this Lagrangian. So the natural question is, can this be used to apply the regravity conjecture logic to quantitatively constrain global symmetry violation, which should somehow have to do with this axion being coupled to instantons. And so let me close by showing you what happens only in pictures. I will jump over the details and show you what the outcome, which I think is very convincing in itself. So if you gauge an axion, or if you Higgs a vector theory with an axion, the following happens. The world line of the charged particle ends on instantons. Instantons then can simply not exist anymore by themselves for gauge invariance reasons. All they are the boundaries of the world lines of charged particles. So whenever you have an instanton, you violate the global symmetry by 1 unit. But the strength with which instantons are suppressed is bounded. X minus S instanton is X minus n Planck over F. We already learned that, at least if I trust the gravity conjecture. But then on the dual side of the axion theory, you have a B2 theory. You know that zero form dualizes to 2 form. B2 forms come with strings, and the string tension is bounded again by this time the magnetically dual regravity conjecture. The tension is lower than some scale associated with the axion. This implies that the cutoff of the EFT is, of course, bounded by the strings. And once you have light strings, there's no effective field theory anymore. So the cutoff is proportional to square root n Planck over F, and then you get a very simple equation. You find that the exponent of minus S is the same as the exponent of minus n Planck squared over lambda squared, simply by plugging in. This was n Planck over F, and then F is, if you solve this for F is lambda squared over n Planck. You plug it in here, you get this result. This is the conclusion. The claim is that systematically derived, gauge-derived global symmetries can never be more precise than this. In other words, if you want a perfectly valid global symmetry, you need to take the cutoff to 0. The height of the cutoff of your EFT tells you how precise the global symmetry can be. If you want a 40 EFT up to a Planck, then global symmetry is violated order 1. And very interestingly, this agrees, although it's a totally different argument, with a plasma-derived or plasma-argued bound by Vishay-Saraswat, and it also agrees with the bound expected from wormholes, which unfortunately I will not have time to discuss. I only show you the pictures. So if you have wormholes in your spacetime, handles like this, you also violate global symmetries in exactly the same way. So let this claim be my last formula, and let me jump to my conclusions for the global symmetry part. Here again is our proposal, and ignore the wormhole stuff. I didn't talk about this. Thank you very much.
Thank you. Thank you very much. So
questions, comments, please. I stopped maybe. You should still be able to see my slides, right?
Yes.
that's fine. That's fine.
They are not full screen anymore. Is that okay?
I can see it full screen. Or okay, they're big. They're big enough.
Good, very good. So yeah, I'm ready for. Sorry for going a little bit over time. Questions? More questions? If we still have time. I mean, you can just whatever you decide, cut or. I hear Manuel. I see Manuel speak, but I just don't hear him because I think he's muted.
Sorry. Yeah. Many times you say parametrically, generically, such words.
Horrible.
Is it true that generically the cosmological constant in string theory is order 1 in string units? That's manifestly not the case. So it's clear that we are living in a very special universe, right?
Yes.
I guess to some extent it makes sense to try to find out just how special it is, how lucky you have to be or something like that. But at the end of the day, it's not really much more than that, is it? As long as you don't have, as you said yourself, as long as you don't have actual strict mathematical things that tell you that this cannot be done, that does the statement that something is parametrically unlikely or most of the time doesn't happen, just tells you that most of the string vacua are not the ones we live in, but that we have known for a long time, I guess. In fact, we live only in one anyway.
I completely agree with your criticism or comment. In fact, I don't know whether you have been here when just at the end of the coffee break, a Heidelberg student already asked me the same or similar question. And I had to admit defeat. You know, this logic is a lot. So I completely agree. As soon as you don't have a proof, or at least the hope for a proof, you can always argue there will be counterexamples. We know we are very special. So why shouldn't we be special in other aspects? So let me try to defend from a very modest perspective. Okay, so the swampland idea or proposal is let's look how extreme string models can become independently of how extreme we need them to become to describe a real world. Let's just study whether there are fundamental limits in what can be achieved. And that is an interesting enterprise for people who have nothing more important to do, like run experiments and measure things, which I agree is more important. But otherwise, it's an interesting enterprise. And it has already taught us certain things. It has triggered us to find problems of KKLT, which we didn't know, which should be resolved. And so in this sense, it is interesting in progress. But whether fundamental progress in the sense of proving a theorem and thereby ruling out certain models is not clear yet. I totally agree. And I'm very worried about this. And I would maybe prefer still to be a string phenomenologist rather than a swampland specialist in this sense.
Okay, thanks.
More comments and questions.
I maybe I didn't understand something about what you said about the gauge-derived global symmetry.
Yeah, ask,
so
please.
My question is: suppose that you return to the initial example of this section of black holes that evaporate. Suppose that we start with a gauge symmetry, where we know that black holes then can be charged. There are the Einstein-Thomson solutions, and there are also cases where the black holes do not evaporate, like extremal black holes.
Yes.
What happens in that case when you send the gauge coupling to 0? Because those objects do not evaporate?
I cannot send the gauge coupling to 0 for the reason of the gravity conjecture. Oh, sorry. You mean you're not discussing now my proposal about the global symmetries swampland?
No,
You're discussing the gravity conjecture, right? Yeah, I understand. Yeah. So as long as there is, so people have thought about this. Let me try to remember what the conclusion was. The conclusion is that you unfortunately appear not to be able to derive or learn anything strong from that. So as long as there is a very, very, so you can go to the limit of a very tiny gauge coupling, right?
Yes.
At the price of a low cutoff. And then you can construct a black hole and let the black hole evaporate. with this black hole to be consistent inside the EFT, the black hole has to be very large because you have a very low cutoff. So you will have, of course, a very weak violation because this huge black hole after a long time evaporates of a global symmetry, but you have a gauge symmetry. Sorry, you have a gauge symmetry in this case. So basically, you are going to be stopped in the evaporation eventually because the black hole has hair, has gauge hair, right?
Yeah, you get the extremality. You arrive with the extremality.
And the extremality will probably, in this case, because there's a very small gauge coupling. Now let me think how it goes. If the gauge coupling is very small, 1 over g, so I think it will be consistent. You will be stopped. You will be stopped fairly early because the tiny g will give you. Let me think. Let me try not to say anything wrong. You could, I think you will not be able to see the problem because you will run into the cutoff. I mean so you now have to analyze at which point extremality will set in. So the mass of the black hole is g times the charge. Yeah, so you will be stopped by extremality only at very small masses if g is very small. So for it depends on how much you charge a black hole. I don't see what you want to learn. I mean, you will not discover a problem. At some point, the black hole operation will be stopped. Maybe it will be stopped in the field theory regime, so we'll get an extremal black hole. Maybe it will be stopped much too late, you know, in the sense of g times charge could be smaller than 1. Then the black hole, which is extremal, will be smaller than M-Planck size. So it basically you never go there, roughly speaking.
Okay.
You evaporate with hair. You evaporate a black hole with hair. Then, of course, no surprise that the charge will be still visible. You know, the black hole will not be, the problem will not arise because the black hole will not democratically evaporate in all types of particles.
Okay.
So I think this has been explored in all possible ways, and it was not possible to turn this either into a contradiction or to derive something from it. That is my memory. Okay, but you should read. There are many papers on this issue which I did not review and do not know very well.
Okay. Okay.
Maybe you can specify your proposal. So what exactly do you want? What kind of problem do you think could arise?
I was just wondering whether, because you discussed, I'm not sure I understood very well your point, but you, in the second point of your conclusion, there is gauge-derived global symmetries, and there are these kind of inequalities.
But that's very different. A gauge-derived global symmetry in the infrared is not gauge.
Yes.
You see, if I make the vector massive, even a little bit, it changes things completely. A gauge-derived global symmetry is not a gauge symmetry.
Well,
in the infrared.
Does that make sense? Because you start with a gauge symmetry, and we also know that in some way, gauge symmetry is not just as a symmetry, it's just a question of how you define the theory. So with the gauge, there comes a lot of other stuff like monopoles and all other stuff. There's a completeless conjecture if you have it in terms of string theory. And once you do and you break it, it still remains a gauge symmetry.
Very good. Yeah, it's a very important point.
You want to make it a non-gauge symmetry in a certain way is not very convincing.
I disagree with that. Here is the formula. Here's the simplest example. Let's discuss this. Can you see, Hans-Peter, this formula?
Yes, yes.
You see the formula.
So this is a very simple Lagrange.
It's not just a question of the low energy effective theory, but there will be, if you're talking about your cutoff, there will be all the other stuff. There will be the monopoles. There will be all kinds of things which come with the gauge theory, all kinds of Wilson line when you go around it, yeah, will be still there, even if you break it in that way.
I agree. Sorry, I didn't
go with G exactly to 0.
No, but I'm sorry. Let's separate two things. In this logic here, I do not take G to 0. I do not consider the limit G to 0. I'm considering the limit that I look at the infrared, in the deep infrared, and all my couplings, G, M, So m is small. The limit is m to 0, if you wish. There's a light particle, and there's a theory. I agree with you, Hans-Peter. The theory is gauged, the U1 is gauged, and fundamentally speaking, in the sense of fundamental Hilbert space, this U1 is always will be gauged. It's a redundancy. There will never be any kind of non-gauged U1 here. I agree with you, fundamentally speaking. But if I cut my spectrum below the vector and the axion, then I have a theory only with this mass, only with this particle m. This particle m has certain interactions. And those interactions are constrained by the rules of this higher energy theory. And they exhibit what appears to be a global U1. As long as I do not allow you to excite the vector and the axion, this theory possesses something that looks to the low energy observer like a set of U1 selection rules.
Well, but
let me. I mean, you know it. I'm sure you know it very well from how you. What happens in string theory? So all these papers in string theory, when people discussed, at some point people discussed the mu term, exponentially suppressed mu term, or B minus L neutrino masses from string theory. This is exactly what happens in string theory. You have some instanton effect, which breaks what appears to be a global symmetry. Originally, the symmetry was a gauge symmetry, but in the commodification process, it got strictly back massive, and the instantons that remain induce operators which violate this apparent infrared global symmetry. That's the effect that we are generalizing and talking about.
I would never see this as a global symmetry. It would be still a remnant of you see, there are the same discussions when we're talking about discrete symmetries. What are discrete gauge symmetries? And what are global discrete symmetries? And there exactly we see the difference, because if you have a discrete symmetry, certainly the gauge boson is gone in a certain way, but still you can make a difference between a discrete gauge symmetry and a discrete global symmetry. So in that sense, I think it's just a question of how you use words. I guess your gauge-derived global symmetries, which you have, I would say, in fact, are remnants of gauge symmetries, and there's certainly coming a cutoff with it. And that will give you, in a certain way, the cutoff will be the mass scale where all this stuff comes up.
Good, very good. Okay, fine. Let me rephrase my conjecture, our conjecture, in a way that would hopefully make you happy. So if you have a Lagrangian with a U1 symmetry, which is not, for which the possibly existent vector is not visible below a scale lambda, okay? Can you agree with that statement? Like B minus L standard model. You have a Lagrangian, or B or L, you have a Lagrangian where you have some U1 symmetry, and you do not see the vector as an effective field series below the scale lambda. Then I claim this symmetry should be broken by operator effects, which are at least as large as x to the minus n Planck squared over lambda squared. This is the claim. So the claim is that if you try to if you find such a situation and you don't discover the vector all the way up to half n Planck, then you must see violation effects in your effective field theory without the vector, whatever that be, for fermion operators, decay rates that are bigger than this. Does it make sense in that phrasing?
Well, I don't understand it. So
why? Sorry, which part?
Well, for example, think about baryon and lepton number.
Yeah, B minus L. Let's talk about B minus L.
B minus L is a gauge symmetry. Is a possible gauge symmetry.
A possible gauge symmetry. I'm talking in this sense. I'm talking about possible gauge symmetries. Yes, good.
Okay, so you're not talking about B or L, but you're talking about B minus L.
Let me exclude cases with anomalies. I mean, anomalies are yeah. You could in principle also involve anomalies, and the the operators that violated there, of course, are visible clearly there. We have an example like this. Let's take B minus L. Yeah.
Yeah. Okay.
So, I mean, Hans-Peter, look, I give you a simple field theory, a scalar, a complex scalar with a mass, such that U1 is unbroken, such that the mass of the two components, real imaginary part, is the same. Coupled to gravity. You agree such model could exist, right? No vector, just this particle.
Well, yeah, okay, good. So
I prefer to say that this theory has a possibly gauged, possibly ungauged, whatever. I call it an approximate global symmetry. I don't see a vector. I see two scalars which can be rotated into each other. I think it's very common in a wide set of people.
Okay, good. So I agree. If you don't care about a UV completion of it, you can call it a global symmetry.
So exactly,
you try to embed that in string theory or so, then as a UV completion, you will probably not be, you see, you will be probably have to change your viewpoint.
But that's exactly what we are doing. That's all what our statements are about. Our statements are about saying that if the symmetry turns out to be embedded in string theory in a gauged way, then there is a trace of that left in the IR. Because it is embedded in string theory as a gauge symmetry, and there's a cutoff and instanton physics and all that, I, as an infrared observer, have a chance to see a trace of that. And the trace are the exponentially suppressed operators that violate this so-called quote-unquote global symmetry, and I can see that in principle. I can constrain them such that I can say what I should look for to discover those effects.
But isn't the actual cutoff of your theorem, F is the mass of the heavy bosons, right? The breaking scale was little f there.
There are two scales where the cutoff, which could be, so which depending on which is lower. You have two scales involved. One is the cutoff due to the axion, due to the strings coming with the axion, and the other is the cutoff coming from the massive vector, sorry, where it was here.
Yeah, that's F now, the mass scale there. So wouldn't you generically expect just also higher dimension?
GF here, GF, sorry, yeah.
G, normal gauge coupling, I take order one.
Yeah.
Wouldn't we normally also expect higher dimensional terms which are proportional to powers of 1 over f squared, which are much bigger than these exponentially suppressed terms?
That's a very good point. The answer is in normal field theory, in field theory model building, yes, always. And there are stringy examples which realize exactly what we are discussing, namely that only exponential effects violate the symmetry. Due to exactly the feature that the symmetries could be gauged in a UV theory, you can have settings where you know that only exponentially suppressed terms will violate that symmetry, not power suppressed terms. That's a very important point. We discuss it not at length, but we discuss in 1/2 page or so in the paper about this. So yes, naively field theorists would expect power-like terms, and I say some symmetries, those which are gauge derived, or as Hans-Peter said, fundamentally gauged, in the UV gauged, only exponentially suppressed terms. It's a claim. I think it's a correct claim. Manuel, feel free to dismiss or criticize further. I mean,
okay.
Good. I don't know whether you want to upload the slides. In the slides, there will be a few more pictures and more examples. I mean, I didn't have time simply to discuss this. There are two examples, normal instantons and one with so-called stringy or exotic instantons, which support this technical claim that there is, I mean, how the models work. I just didn't explain well enough. Sorry, I should have maybe put more emphasis on this last part of my talk, but time has run out on me. Good. If there's nothing else, I mean, I'm happy to close. Whatever you say, whatever you do, I'm happy to answer more questions.
Are there more questions or more comments?
Anybody, please, more comments or questions, also simple questions or critical comments, please. Just shout.
Okay.
It has been long enough, actually, in fact, I think.